Hello everyone. Today we're looking at another Leetcode problem. This is 3307, which is a Leetcode hard problem. Now this problem says that we have to find the kth character in a string game, and this is the second problem in its series. So we solved the first one yesterday. I'll have the link attached in the description. Feel free to check that out. So in this game, Alice and Bob start with a word which is always a single character A, and the way the game continues, especially in this particular setting, which is different from yesterday's, is that we have a new input called operation, which is nothing but a binary array, so it can only have values 0 or 1. And what it means is that if I see 0 at a particular iteration, let's say I have a word AB, I have to take the same word AB and concatenate to this to get the final output AB, AB. But if I see the operations value as 1, what I have to do is I have to take every character in this input word and switch it with the next possible character. So A's next possible character is B, B's next possible character is C. So AB I have to concatenate with BC, that will give me ABBC. Okay, and I have to keep growing this based on the operations um, till we find our kth character to return. Another thing to add is that after I have gotten this output, this based on 0 or 1 evolves. Let's say if the next iteration was 1, so it evolves and it becomes BC, BC, and so I get a new, so this becomes my output, which becomes my input for my next iteration. So it basically keeps growing like this. It just keeps evolving like that. And whenever we see Z, we have to switch back to A. That is another thing that they have told us. So this is the game setting. Now this problem becomes hard because of the constraint. So let me tell you the constraint. So the constraint says that we are trying to so we are looking for k which ranges from 1 to 10 power 14. Okay, what this means is we are looking for the kth character in a word. So a word has to be of length greater than equal to greater or at least equal to k. Okay, and so if we take equal to k, or for the sake of this conversation, what we're saying is that we're looking for a word which is of length 10 power 14. So as long as so when you reach a word which is already of length million and you start now doubling that up, what happens is that you're growing at an exponential rate and very large input. So it's going to get into TLE. So we will have to do something different, like straightforward execution of what they've told us is clearly not going to work. So we'll have to break down this problem into some fundamental concepts and then from there build it up to get the solution. So let's look at these fundamental concepts one by one, right? So the first thing that we should look at is the operations array. Okay, this operations array is of some length. Okay, and if you think about every iteration, what is happening is you're starting with a single length word or a single character word, which is A. Next, you get into the second iteration, and with this iteration, what you're doing is either taking A as it is, or you're switching to the next possible character but you only have one character here. Okay, and so by the end of it, let's say you have AA. Next, when you go to the second iteration, you take this AA and do something to it. Either you copy AA as it is if you had a 0, or you switch each character of that thing, but the len that you're going to be generating is a 2 character. Alright, and so when you combine these two, totally you will have 4 characters at the start of the next one. So now at this point, what you're going to be generating is a 4 character thing. And so at this point, you can imagine it's going to be 8 character. And so you can imagine this is going to be 16 character. So if you look at this, let me just write it at the top. This is 1 character word, 2 character word, 4 character word. So this is length of the word we are generating. Okay, so this is the length of the word that we are generating, which means by the end of any of these operation, the actual word length is double of that. Okay, so you get something like this. So hold this thought in your mind that this is how my operation is working, which is at every iteration I am growing exponentially, but the growth is starting from, let's say this is index 0, so this is nothing but 2 power 0. This is 2 power 1, 2 power 2. So it is 0 index based sequence that I have here in terms of the new word that is generating. Okay, so this is the first conceptual understanding that is parked that there. Now, the second conceptual understanding is going to be around how do we get to the word that, or rather, how do we get to the letter that we need to return without generating all of the possible or the complete word sequence. Okay, so for that, there is something that we should think about, right? Let me explain like this. Okay, so I had A and I created another copy. Okay, so this is the left copy and this is the right copy. Okay, if I have to, let's say it got so I don't know what this is. Okay, let's say I don't know what this is, and if I'm looking at my operation at the first place, let's say it was 1, and that's all I had. Okay, I just had one iteration. My output is 2 character long. That's all I have. Okay, but I don't know what is this output. I don't know what is this output. Okay, but there are 2 things I know. I know that this is 1. I know my k is equal to 2, and I know that my base value word always starts with A. Okay, so what I can do is split this into left and right. Okay, now I know that my word exists here. If my word exists here, okay, what I will do is I will look at the change that I made to get to this point. The change that I made to get to this point was a shift. So let's say I have a shift counter that gets incremented by 1. Okay, so now I have k equal to 2. I have processed this particular element, and now I am ready to go look backwards at the state which created this state. So what was this particular state that would have created this state? Okay, so I'm ready to look at this state now after processing the right state. Cool. So I have processed, I have taken a note that I need to, whatever was here, whatever was on the left hand side, I need to shift it by 1. And now I need to go back to checking what was it here. So let's do that. k minus how many elements should I switch back? 1. And that gives me 1. And when the length is just 1, what is the character that I can have? I can only have A. If I can only have A, and if I have to shift it by 1, then what is the output that I will get? The output that I'll get is B. So that happens to be my output. Okay, let's look at a little more now. Let's say I had, let's say I'm looking at 3. And so I start, this is 2 character, this is 2 character. Okay, my 3 is here. Alright, now let's say my op was something like this. Okay, so now I am looking at this index and I know it is in the second half. Now second half was processed with some operation which was shift. So let me say shift counter is equal to 1 now, because I know whatever I got in the previous state, I have to shift it. Okay, so that's the track that I'm maintaining. So I have to shift this, and now after processing this and understanding how many times the previous state would have gotten shifted to get me this, I am ready to now process this state. Okay, so what would you do? K is equal to 3. 3 minus 2, if I have to subtract this, that gives me 1, which means on the left hand side, this element would have been the first element. And the first element, after shifting, got to some result. And that is what I have to return. So now that I have processed this, I am looking at this. Now k becomes equal to 1. And we know when length is 1, there is only one possibility, which is A. And now I have to apply one shift. So that gives me B. So this is the logic that we're going to implement. Let's look at another example, and let's look at an example that is given in the problem itself. Okay, so the problem has this example. K is equal to 10. Operation is equal to 0, 1, 0, 1. Okay, so what are we going to do here? We are going to look at we're going to look at the left hand side count, and we're going to look at the right hand side count. Okay, how do we do that? So the previous examples were handcrafted, so I could tell the left size and the right size. One thing is for sure, that these two sizes are going to be same, because we're growing by 2, so they have to be same size. So what is the size going to be? Let's figure that out. Now 10, if I write it in binary, okay, let's say 0, 1, 2, 4, 8, it can be written as 1, 0, 1, 0. Okay, and what is the length of this? The length of this is 4. And so the length of this is 4. This is nothing but, if you take the powers, you get 2 power 3 plus 2 power 1. I am interested in this power, the power of 3, because if I subtract this, then this is what is half and half that we are creating. Now 10 is greater than 8, that's why it's on the right hand side. So the half and half that we are creating here is 8 and 8. Alright, so the way we do that in Python is take k, take bit underscore len, and that gives you 4. And then from that, you subtract minus 1 to get your exponent. You got your exponent. So you know your left hand side is of 8 characters, your right hand side is of 8 characters. Okay, now in that, k is equal to 10. So this was 9 10, 11, 12, so on. So we know that this was my input, and I used my operation on this to get this part, the right hand side part, and then I concatenate the two. So what operation did I do on this? I did the operation 1, which means every character that I took, I switched it to the next possible character. Okay, what does that mean? Whatever this character came from, it had to be switched to the next character. Okay, fine. Let's say the character that this came from was X. That means this had to be switched to the next ix plus 1 in its Unicode value. So let me write down here. So my shift counter right now is equal to plus 1, because we're going to keep backtracking like that. We're going to keep backtracking what was the position of this current k that I'm looking at in the previous output, which became the input. What was, and then I will do the same process again. For the previous position, when I go back to its left, which was its input, what was the position in that? And then you keep going back till you come to k equal to 1. And from there, you have already counted the number of shift counters. So you just keep shifting till you get the character that that you wanted to get. Okay, so after this iteration, what happened? What happened was we identified that this is the character k equal to 10, which is in the right hand side. It had been applied operation of 1. So what is the position of this character in the left place? That is going to be k minus 8. 10 minus 8 is equal to 2. Because if you think about, you are just taking this and offsetting it by 8, so that these values shift down to these values to give you the case value in the previous position, which happened to be 2. Okay, so remember, this is going to give you 2 power 0, 2 power 1, 2 power 2, 2 power 3. So when you were at 2 power 3, when you were at 3, 4 minus 1, 3, when you were handling this exponent, you used this index. Okay, and now you're down to 2. So you will skip this and you will directly work on 2 power 1. Okay, so now our k is equal to 2. Let's look at its bit length. This has a bit length of 2. That means the exponent that we're going to be looking at is 1. But there is one catch here. Okay, so it's actually not going to be this, not going to be that. It's actually going to be directly landing at this. The reason for that is, let's take the previous example itself. Okay, when we had 8 and 8. When we had 8 and 8, our 16 was here, which should have gotten mapped to 8 here. Okay, but what happened is, because 16 is here and 16 is one extra bit length, so if you take 16, that would be 16, 8, 4, 2, 1, 0, 0, 0, 0, 0, 1, and this is 5. So when I subtract 1 from it, I get 4, which is to say 16 and 16. That is not right, because I am at 16 position. I want to find the corresponding left hand side. Okay, I cannot have it on the left hand side. That doesn't make sense. Okay, so I want to find the corresponding left hand side of this 60. So what we do is, only when we see powers of 2, Only when we see powers of 2, we are going to subtract additional 1. This gives me 3. So now I have 8 and 8, 16 setting that I wanted. Now same way what happened here was we got 2. Okay, since we got 2, we were computing bit length is 2, exponent is 1. But we cannot have 2 and then another 2 and from here try to figure out like where it went. This needs to be broken down further so I can find, because if this is 2 and 2, then this is the entirety of it, right? But I don't want it like this. I want to split this up into 1 and 1 so that I say this 2 came from this character, which is why I'm going to take this bit length and we're going to do minus 1 by default. But because this is a power of 2, I'm going to do an additional minus 1. So we split it up like this so that this power of 2 is actually on the right hand side and I'm able to map it to its left hand side. Okay, so we do that, and so the power that we will look at now is going to be the 0th index, and we're going to skip these two. Okay, and so so we come to the 0th index, we see it is already 0, so my shift counter has not increased, has not incremented, and so I have to just take A, my returning my result. Just have to take A and shift it by 1 to return B as my answer. That's it. It might seem a little confusing. It is actually a little confusing if this concept is new to you, but once you understand this, the code is pretty straightforward. So let's write the code now. So find kth character. This time we are given k, which is an integer, and we are given operations, which is list of integer. And what we are expected to return is the kth character. So we are going to be returning a string. Now for this, my starting state, like before, is just A. And my shift counter is equal to 0. Now, while k is greater than 1, because when k is equal to 1, I know the output. When k is equal to 1, my character at that position is always A. So if it is greater than 1, only then I have operations applying, so I need to evaluate that. So I'll take t equal to k underscore bit length and then minus 1. But if 2 power, or let's write like this, if 2 power t is the same as k, or for the sake of neat readability, let's say if k happens to be 2 power t, then in my calculation this is going to appear on the left hand side, but no, I want it on my right hand side so I can map it to a value in my left hand side. So let me decrement this value by 1. After I have done that, now let us look at the operation value at this index that I computed. So if operations of t is equal to 1, then I increment my shift counter. So my shift counter becomes increments by 1. Okay, and my k now decrements by half, which was more than, basically by a power of 2. Alright, and then finally I will return the character, but before I return the character, let me do the Unicode operation, which is take the Unicode of A plus take the shift counter, and the shift counter for a very large operation can be greater than 26, so take modulus and then add it to the Unicode value of A, and then from the derived Unicode value of A, which is this, give me the character output. That is what is happening for in this problem, and so the this is the solution. And if you think about the time complexity, just like how we grow the word by powers of by 2 times every time, so 2 becomes 4, 4 becomes 8. Here we are halving. 8 becomes 4, 4 becomes 2, 2 becomes 1 in the worst case. In the case that we did with k equal to 10, we happen to jump few more, we happen to jump much larger thing. So my time complexity for this will be log k. Yep. That's it for today's problem. I'll see you again with the next one. Thank you. Bye bye.